Okay, morning everyone. So good afternoon. Today our speaker is Héctor Jardón Sánchez. So Héctor is not working so far from us, like just 2 floors below in Jagiellonian University. So he's more doing some probabilistic group theory. So and he will give us today some introduction to unimodularity. And it has some application and connection with infinite graphs, especially quasi-transitive graphs for those who know them. And so Héctor also did his PhD. He defended quite recently in Leipzig.
Yes.
And now he's doing a postdoc for second year. So please, Héctor.
Okay, thank you. So, first of all, I wanted to say that this talk is based on a joint project that we recently uploaded in Archive with Laszlo Marton Toth from Renyi Institute. And before we get into what's going to be the math, which I promise is going to be fairly introductory, maybe let me say a few words of how we ended up here, because then we probably don't come back to like the paper itself unless we do have time. So the whole point of this project that I had with Lazzi was to study the interplay between two kinds of spectra on these unimodular random graphs that we're going to talk about. They will be introduced later, at least in a hand-wavy way. And for these graphs, which could be some families of quasi-transitive graphs, we have two kinds of spectrum. One is local, which is the usual little L2 spectrum. And another is the spectrum that we get from running stochastic processes on this graph. So we assign some random labels to the vertices of the graph. And based on those labels, we make some decisions of which number to assign to each vertex. And basically what we proved in this paper, which we called Skeletons and Spectra, is that there is a sort of Alombo-Pana bound that controls expansion when we talk about these random labelings, and the factor of IID, so the independent identically distributed labels, give you the Ramanujan version for this Alombo-Pana bound, at least in some relative version. And improving some results in this paper is when we entered and encountered the need of characterizing these graphs for which there exists a free quasi-transitive action of a free group, and we gave this sort of intrinsic or purely geometric characterization, which is as unimodular quasi-transitive quasi-trees. In this, Hugo was very helpful in sort of guiding us through some of the literature that you may be more familiar with than I am. And that's more or less where the paper, what the paper is about and how we ended up here. But really what I'm going to talk about today, I'm just taking this as an excuse to talk about unimodularity. And why am I coming here to sell unimodularity? Well, unimodularity is roughly in quasi-transitive graphs is a property that basically comes to say that we can count the vertices of the quasi-transitive graph in a way that they are all taken into account fairly. We will make this precise. We will actually give 4 definitions of this, so we will be introductory. And unimodularity is a central assumption when doing probabilistic graph theory or studying stochastic processes on Cayley graphs or in unimodular random graphs. So it's central to sort of communicate or understand what we're doing in the random walks group. And also unimodularity arises when one is studying a probability measure preserving dynamics. So I think it can also serve as a bridge from graph theory to what the people in the dynamics group do. So I think that motivation today is we're going to introduce this notion. I think it's interesting and it can maybe help to set a bridge between the theoretical computer science group and what other people are doing in the department. So now let's get into the math. So let's first go over the theorem that we have here. That's going to be our motivation for today. And then we're going to start defining everything and eventually running into unimodularity. So the theorem is the following. We have a connected graph G is my graph, it's connected, it's countable, can be finite, but it's going to be infinite. We're going to be typically thinking about infinite graphs today. It's locally finite, we will define what this is in a moment, and then the following are equivalent. We have a dynamic characterization or more algebraic characterization. There exists a free and quasi-transitive action of a free group on this graph. And then equivalently, we have an intrinsic or geometric characterization, which is the graph G is unimodular, quasi-transitive, and a quasi-tree. It's quasi-isometric to a tree. So let me now go over all the words that I've said here and start making sense out of this and setting some notation. So the first one is G is locally finite if for every U vertex of G, the degree of U is smaller than finite. It's finite, not surprising. Then just to recall everything, if we have an action of a group gamma acting on my graph G, we say that it is quasi-transitive. If there are finitely many orbits, in that case, because it's locally finite, let's say of vertices. So when we look at the vertices and we quotient out by the group, this is some finite set. So there are, we can think of the quasi-transitivity as there are only finitely many pictures, finitely many types of vertices. When I sit in a vertex and I look around me in the graph, I can only see finitely many pictures. And then this is for an action. What is a graph quasi-transitive? We say that the graph G is quasi-transitive if its automorphism group which we call AUG acts on the group quasi-transitive. Okay, so this does complement the picture of I sit at a vertex. From the vertex, I can see different pictures of how my surroundings look up to isomorphism. There's only finitely many pictures. And so we have quasi-transitive, we have this. Now we go to a quasi-tree. So I think that you've been familiar late, yes.
You might also give a reminder of free group.
Yeah. So before I go there, the free group is just the group generated by D many generators and no relations. So a typical element of the free group, say we have F2, an element is a word A, B, A, and now if I put A minus 1 again, this is a legal element, but these are the only things I'm allowed to cancel. Other than inverses, I'm not allowed to cancel. So B minus 1, maybe. So these are like the words we have, and when we multiply two words, we're just putting them one after the other. Okay? There's this perspective of the Cayley graph that is very useful when analyzing graphs. So what is this, how you can look at multiplication in this free group? You have this infinite for regular tree, very infinite, and then you also have these labels on every vertex, A, B, and so on and so on. So how do you read this word A, B, B, A, B? Well, this would be A, B, B, A, b minus 1, and you would end up somewhere around here. And then if you want to multiply by some other word, now you just start there. Okay? Yeah, and the automorphism group, of course, just to be sure with everything, is the bijections, the graph homomorphisms that are bijections in respect to the graph structure of the graph onto itself. So what we were going to define now is, more questions? No, okay, we were going to define quasi-tree. So this is a tree, and now you're familiar with quasi-tree, so I could just say, oh, quasi-tree is, if you look at it from afar, it looks like this, more or less. So quasi-tree, maybe G is a quasi-tree if it is quasi-isometric to a tree. So what does this mean precisely? This means that there exists a tree there exist constants A, B, C, and there exists a map phi from the graph to the tree such that distances are preserved coarsely. So the distance of the image of two vertices is controlled above by some linear distortion. This would be distance in G, this would be distance in the tree, plus some error, and the same in the other side. So, UV, and now you also subtract this term. So distances are distorted linearly up to like maybe some big error. So the classic example is the real line and the lattice of the integers. Distances are the same, but you just need to correct that an interval maybe is collapsed into a point. And apart from this also, like in the lattice of the intervals, I want to be able to every vertex of G reach every vertex of T at least up to some thickening. So apart from this condition, I'm going to add that for every W vertex of T, there exists some W set in the vertices of G such that the distance from the image of set to W is at most this constancy. Okay, and this is for all vertices. Okay, so I think that makes all the definitions except unimodularity, which is the main one. And that's the one I want to go into now, I think. Yeah, correct. So before we go into definitions of unimodularity, I'm going to give you two examples of graphs. One of them is unimodular, the other one is not. And in the unimodular one, we will see why this theorem also makes sense. So like, let's first do that. So our first example is going to be the 3-4 biregular tree. So let T3-4 be the biregular tree with degrees 3 and 4. What do we mean by this? There are two options. We have two kinds of vertices. Vertices of degree 3 have 3 degree 4 neighbors, And alternative vertices of degree 4, they have 4 degree 3 neighbors. Okay, so once we'll draw it, can start here. I have degree 3, and now this must have degree 4. And now each of these again, this has degree 4, so it has to be connected to degree 3 vertices. So these guys have degree 3. So something like this.
So if I understand correctly, this is quasi-transitive.
This is quasi-transitive. There are 2 orbits, exactly. When we look under the automorphism graph, we have the root, not the root, we have the degree 3 vertices, and we have the degree 4 vertices, because this is infinite, so the picture continues on and on. And this is the first example where we can easily find out this free group, but it's not trivial, because remember, if we take regular trees are the Cayley graphs of free groups with even degree. So in that case, for instance, for regular tree, the sort of theorem holds trivially, right? This is already the Cayley graph of a tree. So how do we find an acting tree in this specific example? And basically, this is the whole picture that one's trying to extend in the theorem. This graph is the universal cover of another usual suspect that we have. So this is the universal cover of the K3-4 graph, right? So this is the complete bipartite graph where we take 3 vertices on one side, 4 vertices on the other, and it's complete bipartite. So this is connected here. Okay, and now if you remember from the courses in algebraic topology, we have that. We will do a picture and you will see how it makes sense, okay? But let me just remember.
You are assuming that of us had a course in algebraic topology.
Oh, so I always thought that people were like mathematicians. Here in the seminar, we're mathematicians doing graph theory, but I see that they are really computer scientists. Okay, then this is very cool stuff on what you can do with homotopy theory, and we will just do some picture and it will make sense, okay? So
what does it mean, universal cover?
The universal cover means basically for a graph, anytime you take a finite graph, there is some tree that has this surjective graph homomorphism onto it. And as in this way, in here, there are vertices of degree 3 and vertices of degree 4. And this is a tree. So this tree always exists for any finite graph that you consider. And the existence of this tree, you can think of it as coming from homotopy theory, that you can construct it sort of explicitly, as we will really be doing. We will sort of be constructing this.
So what it means is that, first of all, there is a subjective homomorphism.
Yes.
From left to the right.
Yes.
And is there some universal property?
The universality property is that once you have another cover, in the sense of graph homomorphism, surjective graph homomorphism, you don't want things like I'm taking 2 edges like this and folding them like that. It needs to be a cover, but once you take an intermediate cover or another cover of this one where you sort of take some loops and break them away, then this guy will still be covering that one. So it's a cover for any other cover that you can consider. And it's a tree because in some sense, you obtain covers of this guy by taking loops and either like enlarging them or either breaking them into a line, right? So if I have like a triangle, maybe I turn it into an hexagon or maybe into a line. And you get a tree when all of the cycles that you have in here, you've really broken them out into lines. Okay? So we will see how this arises. So the theory is, yeah?
There's a small comment to say that this surjective automorphism it should be also locally injected.
Yes. But maybe you can take this as the the neighborhood is mapped injectively. Yes. So how does this work? Basically, like what's the recipe now? The recipe to compute this fundamental group, as they call them, is the following. You consider your spanning tree of the graph, okay? So we take a spanning tree. So maybe I'm going to take this one and just start doing a search from here. And now I haven't reached this one, so I'm going to do it with my next guy. Who is this guy? Okay, so I have my spanning tree. Okay, this is some spanning tree for this graph. And then you have some remaining edges. Each of these edges gives you these fundamental cycles. And these fundamental cycles are precisely the generators of your homotopy group, whatever that is. So in particular, what is the case in here? We have 7 vertices. This implies that a spanning tree has 6 edges. And in total, we have 12 edges. So this implies that there are 6 generators for our free group, okay? So there is an action of F6 on T34, okay? This would be the calculation that you do knowing homotopy theory, but let's look at what's really going on, okay? Let's do the picture. I'm going to first enumerate those guys, and I'm going to leave them up here. Okay, so I'm going to take 1, 2, 3, 4, 5, 6, 7. And you can think of this as really how I would be constructing this universal cover, okay? So I start with this guy. He's a degree 4 guy. So I'm going to say, okay, this is my guy here. Now, do I want to? Yes, okay. Here's my guy here. He's connected to 4 vertices of degree 3, which are precisely the 7, 6, 5, and 4. And these are the leaves, so I'm going to put them like this. So I'm going to say this one's the 7, this one's the 4, 5, and 6, okay? If you want, I'm sort of saying where is each of these guys going to be mapped, okay? And now I have, okay, 6, 5, 4, they are leaves in the spanning tree, and now 7 is connected to 2 and 3, okay? 2 and 3, okay? So this would be defining the fundamental domain of my action, and this is giving me a lift of each of those guys into here. And now we need to sort of say, how does this continue? How does this labeling continue through the whole infinite tree? Or how do I get my action of the free group? So to do this, I get one of these fundamental cycles, okay? So which are the fundamental cycles? The fundamental cycles, I get them when I take an edge outside of my spanning tree, okay? So let me maybe, for instance, take this one. Oh, no, this one. This is not nice color. Okay, this is just too much colors. I take this set, okay? And what is the fundamental cycle that it gives me? I take these sets, and now I take the unique path in the tree that connects these two. So it's this thing here, okay? So what is this reading like? This is reading, you start from 1, and you go to 7. So this leads to a path. You start in 1, you go to 7. From 7, you go to 2. I'll do it starting from 6. It's going to be easier to draw. You start in 6, then go to 1. Then from 1, you can go to 7. From 7, you go to 2. And now you go back to 6. But now there will be a 6 here, but what I do is there is another 6 in here. And I can choose any of these 3. It can be here. And now there is a new label here that does 6. And this gives me the transformation that I want. Now I have what one of these elements of the free group is doing in here. It's saying it's taking this 6 and it's mapping it up to here. Once you do this with all these 6 fundamental cycles, you will be reconstructing how each of these edges is moved where. Okay, you can also do it with the 1 now. Now the 1 is going to do 1, 7, 2, 6, 1. So now you have 1, 7, 2, 6, and then it's going to move into 1. So now you know where also 1 is. And in this way, you can expand this fundamental domain that I started into the whole tree.
So this is describing how this element, like this blue edge of the free group, how it acts on a single vertex.
Yes.
Yes, this is kind of describing an action.
Yes.
And then if you have like an element of the free group, which is concatenation of several of those generators, then you just continue going.
Exactly, you just continue going. Exactly. So
how did you choose the direction? Because like when you have this fundamental cycle, you started traversing it in a specific direction.
Yeah, this is up to you. But otherwise you will get the inverse. So because it's a group, you have like the element A and the element A inverse. So I declare one direction to call it A, and the other direction will give you A inverse.
And it doesn't matter which one.
No, in the end, because of you need an inversion, you will end up with the same result. And then in this way is that you start with this graph, you end up here, and then, well, the thing is that it's the notion of basis of cycles, right? The notion of basis of cycles is what is saying these fundamental cycles associated to the spanning tree are independent of each other. There's no relations between them. And that's the notion that once you translate it to the group that's acting here, says this group is free. Okay? Questions? More questions? Okay, so let's move on and let's go into what is not unimodular. So in particular, a posteriori, having the theorem, we can say, okay, this tree is unimodular. That's good, but what is an example of something that's not unimodular? And let's leave it here so we can prove that it's not once we have the definition. And the classic example is this so-called grandmother graph. This grandmother graph is as follows. You start with a infinite three regular tree. You start with an infinite three regular tree and you choose one end. So for instance, I'm going to choose the end of the tree that goes to the top. And here, this is one of the main messages of today. When you say choose an end, you've ruined unimodularity. That's one of the first messages. Like in unimodularity, in a sense, all directions count the same, count evenly, and there's no positive or negative directions. The moment I say pick an end, unimodularity is oftentimes, or most of the times, dead. And what I'm going to do now, because I don't want to have a directed graph, I'm just going to...
And it's an infinite path.
Yes, an end is an infinite path, so in this picture that we've done of the three regular tree, you can always take any vertex and sort of always go up. And what I'm going to do to encode this choice into a graph structure is I connect every vertex to its grandmother. So this guy is going to be connected here. Maybe I'll do it different color. So this guy will be connected here. This guy will be connected here. This one here. This one here. 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 And this one's also connected up. And of course, there's more. You do this all around, but I'm only going to do this to not cover the board too much.
And you keep the original edges.
You keep the original edges, yeah. So the result of this is a transitive 8 regular graph. But it has this specified direction, with a specified direction. And this specified direction is that once I take my vertex, if I look at the triangles that I see from that vertex, I see this triangle, I see this triangle, and if you do the adjacency relation of these triangles, you will see that this triangle that I have on top is special. And only from looking at the graph structure, I can highlight, hey, this guy, this triangle is special from these other triangles. So there's a preferred direction, go up, okay? And that's what's going to mess up unimodularity. And now we're going to define it and see why this breaks this property, okay? So maybe here, maybe here we go into section 2, which is unimodularity. And so when did we start in the end?
20 past.
20 past, okay.
You really...
Okay, good. So now the point in this part of the talk, I forgot one thing. Let me sort of comment it quickly. This result that we have doesn't come out of the blue. So there are many results that characterize this quasi-transitive quasi-trees. Perhaps one of the most classic is this Schramm and Müller, who says that a graph G is a quasi-tree if and only if it only has these thin ends. So anytime you go to the one direction at infinity, you can disconnect it using cuts of small size. And there's the one of Hamann, Lehner, Miravtav, and Ruman, which is the one we used there, which says that such a quasi-transitive quasi-tree has a terminal factorization in terms of finite graphs. So they have a procedure of cutting the graph, doing a tree decomposition, and if you continue applying this tree decomposition, at some moment it stops into a tree decomposition with only finite bugs, okay? And that's a key ingredient in this theorem. And that's what Hugo helped us decipher how to apply because it was a bit hard to translate for us. And there's many other results. So there's results of Javan Tolim, Manning, Vos. There's many characterizations of quasi-trees, okay? So this is not coming out of nowhere. But now let me go into unimodularity. So my next goal is to give 3 definitions. Later, if we have time to do the proof of this, we will have a 4th definition, but that's very group theoretic. So now I'm going to give you 3 definitions with a more graph theoretic flavor or computable flavor, so that if you want to understand this property, you can prove that a certain graph has it. So we're going to start with transitive graphs first. So I want to start with transitive graphs so we can give a first proof that this is not unimodular, and then we will evolve into other definitions. So a transitive graph D is unimodular if for every x we have that gamma x y equals gamma y x. What do I mean by this? Sorry. In my notes I call them, this is gamma u v, this is gamma v u, where gamma is the automorphism group and gamma u denotes destabilizer of u. Okay, so what is this? You sit at the vertex u, you take an edge, you sit at, yes?
You ask this to be finite or something?
This is the stabilizer, and this is the stabilizer acting on a neighbor, so it can only send it to neighbors. So it's finite by construction because we're only taking locally finite graphs.
Stabilizer is all automorphisms which
fix this point. Yeah. And now what we're asking here is I take an edge, I sit in one of the guys, and I start applying automorphisms, and I see where the neighbor goes. It goes to a number of elements, and I do the same from the other side. And I should see the same picture in the sense that there shouldn't be a quantitative difference between the two directions marked by this edge. Okay? And this is easy to see when a graph, this is an easy definition to use to see that a graph is not unimodular, because we can now, for instance, see it here. Okay? So I'm going to take, this is going to be U, and this is going to be V. Okay? So I'm going to look first at gamma U acting on V. How many guys we have here? Well, I take U, and now where V can go, V could go to this guy or this guy, but they cannot really because of what we said, that this triangle is special. There is this marked direction to the top. So if I take an automorphism that preserves this direction, this guy V, keeping U, cannot go down here. Therefore, when I look at the stabilizer of U, it fixes this guy. But what happens when I do otherwise? Well, now I have the same picture here. And now U and this other guy that I could call U prime, they are both sitting in the same picture with respect to this end. So the stabilizer of V can flip these two things, preserving an automorphism. And I have two. So because they are different, this implies that this graph is not unimodular. Okay? And a similar argument, you have, I think this may be familiar for some of you, a similar argument holds for these distal leader graphs. These are graphs in two parameters, and we take different parameters. This is just in case you're familiar with these graphs. So we have this definition, first definition of unimodularity. It says anytime you take one edge, there is no quantitative way of choosing one of the two directions, okay? And what this goes into, which is the definition I'm more familiar with and you will hear all probabilists talk about, is the mass transport principle, okay? So now we're going to define unimodularity for these quasi-transitive graphs and give this mass transport principle. So basically what the failure of unimodularity is saying here is that even though the vertex is transitive, vertices that go up are heavier. In what sense of heavier? In the sense that I have these two guys which, if every vertex sort of weights 1, they both have mass 1 and they could send this mass 1 to this guy, but this other guy which is on top is not automorphic to this other two. So then this vertex has to be heavier. So that's the idea that's captured by the mass transport principle, which says in a transitive graph, if you send some money, say every vertex sends some money to other vertex, only paying attention to the graph structure, then the expected money that goes out is the same money that goes in. And this would fail in this case, because if every vertex says €1 up, or 1 zloty, then when you go up, everybody's sending 1, but everybody's receiving 2 at the same time. So that's the problem. And now let's make this precise. And to make this precise, we need to talk about this local perspective on graphs. So we need to talk about rooted graphs. So a rooted graph, this is just some terminology that will be helpful for the language we're using. A rooted graph is just a pair G-O, where G is a graph and O is a vertex in the graph. And we want to look at all the possible configurations of this up to isomorphism. So I'm going to define this fancy D with a dot, and this is going to be isomorphism classes of connected locally finite quasi-transitive graphs, rooted quasi-transitive graphs. Okay, so by isomorphism of rooted graphs, what I mean is not only there is an isomorphism that takes G to the other graph, but also takes the root to the root. So in particular, and this is a slight abuse of notation, if G is quasi-transitive and U and V belong to the same, in the same orbit, then when I look from this perspective, they are the same element, okay? And I'm going to be saying that GU equals GV, because from now on, I only want to look at the graph structure. Okay, so I'm going to have my quasi-transitive graph. I'm going to take a vertex, look at the configuration that I see around me, and that's what I record. Okay, I record that isomorphism class. So if I take two equivalent vertices, the structure that I see is the same. Okay, and this is some maybe unfortunate abuse of notation that's always going on in the literature. And because I want to be sending money from vertices to vertices, I'm going to do the same with doubly rooted. vertices. Okay, so a doubly rooted graph is just going to be a pair G, U, V, a triple. And now what is this? This is, I'm taking my graph G, I'm taking a root U, and now I'm taking some other vertex V. So I have this configuration of 2 points. And my isomorphism family is homomorphisms of the group that map both roots to both roots in the order they are. So, for example, this one with this one would be the same configuration as if I take this one with this one in the graph. But if I revert them, they are not the same, okay? So this is depending on the order. This one first and this one second is not the same as this one first and this one second, okay? And similarly, I'm going to define, and I let G, fancy G with 2 roots to be defined similarly as well. So you take all isomorphism classes. Okay. Any questions about this? Okay. So now I can define what unimodularity is for a quasi-transitive graph. So let G be quasi-transitive and let me maybe call X this just the different types of vertices, okay, just for notation. Then G is going to be unimodular. Then G is unimodular if there exists mu, a probability on X, okay, and what is a probability on X now? X is a finite set because this is quasi-transitive. This can of course be made more general, but for the purposes of the talk, it's just a family of weights that are non-negative and add up to 1, okay? And what I have is, with this rule of sampling vertices, okay, for any payment function, so let mu a probability on X such that for every payment function, and what is now the payment function? The payment function goes from here to the positive real. So I'm taking on my graph G, I'm taking possible configurations of 2 vertices, and whenever I see that configuration, I say, okay, along this pair, I'm going to send whatever amount of money, okay? Then what I want is this mass transport principle. Okay, so this is mass transport principle. And it says that the expected when I sample X from mu, and now I look at all the vertices in G. So I will write it and then we will make sense of what's in here, okay? Okay, so let's see what it says here. F of ux, G is just telling me that I'm in the graph G, okay? that's even irrelevant. We wouldn't need it. And I'm going to think of this number because I'm coming from algebra. Ux for me is going to be x send some money to you, okay? So this is, I'm taking a random x from my graph, and I'm looking over the graph and counting how much money x is sending. So this is just outgoing mass for x. And you're taking an expected value over that. And in this case, as we will do later in example, this expected value is just a sum with weighted sums. And now this is the corresponding thing, but inverted. Okay, I'm taking a random x, and I'm looking at all the other vertices in the graph, but now this is reverted. So this is mass that v sent to x. So this is ingoing mass to x. So what the mass transport principle is saying is the expected mass that goes out for any of these payment functions is the same as the expected mass that goes in, okay? And now we're going to do some examples. Yes?
Don't you want some kind of invariant function on f in order to well define it? Because you define it on the orbit, that is an entire class. So you want something like if you have like a pair of roots, but
No.
two pairs which correspond to the same orbit and they have the same values. Well,
Because f, that's a very good observation, which is maybe hidden in the notation. F is a function in g dot dot, and g dot dot is isomorphism classes of pairs. So when you feed f the same configuration, it needs to give the same output value. Okay, so that's a very...
It means that you are counting each such configuration only once in the summation. Right?
In here, you can have it in different ways. In here, I'm actually counting them several times. But typically, you will do this. You could even only take, to define this, only take the neighbors.
But this will be an infinite sum.
Not necessarily, because this is, okay, that's why it's here. If this is infinite, this will be infinite. That's what I'm also saying here. If one is infinite, the other one is infinite. But the non-infinite examples are, for instance, when you only look at the neighbors, or you only look within a certain radius of the ball. But yeah, this works also for infinite. If one is infinite, I also want the other one to be infinite.
So you're actually summing over all the vertices.
Yes.
Here you are applying the function to the isomorphism class of this GUX.
Yes.
If for many vertices you are getting the same isomorphic class, then
yes.
you are taking the tail with multiplicities.
Yes, exactly. Because what we're saying here is we're taking this local perspective. So f is defined, we can think of this as the graph not having any kind of labels. So once I take the two vertices, the only information that I have is the combinatorial structure, and it's only based on that f decides the output value. And that's what we're having here. So let's do some examples to see where this makes sense. So perhaps the first example is Cayley graphs of groups. Okay? So first example, Cayley graph of a group gamma. In the case of a Cayley group of a group gamma, okay, this could be the tree that we were considering before, the regular tree, the four regular tree for F2. What is mu? Well, this graph is transitive. So transitive implies that I don't really need to care about mu, because mu, there's only one orbit, so mu can only be one. So what does this whole expression reduce? It reduces to me looking at this sum. All the elements G, well, gamma, in my group gamma, and the function f when we set mass from the identity or the root. I fix the identity and I go to some element gamma. And this identity could be any other guy because there's only one R. And I go to some other element gamma. And what I'm going to apply now? Now my goal is to say this thing should be equal to reverting this, okay? So my goal would be saying that this is the same as the amount of mass that goes from gamma to the identity, okay? This is what we want. And the trick in here is that I have an inversion. That's what makes the group special, and I don't have, for instance, here. I have an inversion, so I can just say, okay, just invert the whole thing. The group is the same when I invert, so this is the same if I take gamma minus 1 E. And now is where I'm using, as you very well pointed out, that, okay, this is E, say, and this is gamma. So this is there and there. This is gamma. And now gamma minus 1 would be here. Okay? So now from E to gamma is the same picture of when I'm going from gamma minus 1 to the identity. Therefore, this is the same configuration. And the fact that F only depends on the isomorphism class gives me that this is actually equal to F of E gamma. I can multiply the whole thing by elements and get the same result of F. And now I have the desired equality. Okay, so all Cayley graphs, graphs are unimodular. Okay. Here, well, I pointed it out before, and I'm just going to say it out loud. Every vertex sends mass 1. My function f says I send mass 1 to the next guy, to the successor. So if this is u, say that I call this u plus, okay? And I consider, let me erase here maybe. I consider as my test function f of v u is equal to the indicator function of v is this successor to u. Okay? So I'm only sending money to the next guy. Again, because the graph is transitive, there's no problem with the probabilities. But now what happens when I look at the sum over all vertices and I look how much mass I send from a fixed root? Well, I'm only sending mass 1 here because I only send it to the next guy. However, when I'm looking at how much mass I receive, this guy u is the successor of this guy, but also the successor of this guy. So it's receiving money from two guys. And as you can see, this is the same failure that we had with the computation of the stabilizers. So these are different, and again, we have that G is not unimodular. Okay? So we're into 1 hour. So I'll ask you, do you prefer to do one more definition of unimodularity, or should we talk a bit about the proof of the theorem? So we can finish sort of within a reasonable time. The other definition is once you have this such a mu, as you have defined here, you can sample a random edge, right? So you first sample a random vertex, you average by the degree, you weight by the degree, and then you sample a random edge. So this gives you a distribution to sample random edges. And you can reverse this distribution. You can sample the random edge and then revert it. So unimodularity is when this distribution on edges is invariant under this involution. That's the other definition. You can find it in the usual references for this, like there's a book of Lovash where unimodularity is very well introduced, Lyons Perez for a more probabilistic approach, and in there you can, for instance, see this other definition. So, maybe let me just say that regarding these two definitions, this involution invariance ones I will not present, perhaps is one of the easiest ones to prove because it gives you a way of constructing a table with numbers and you check whether certain numbers are the same. So it's easy to sort of prove that something is unimodular. But when you're doing proofs, typically the mass transport principle is your helping tool. Okay, so then maybe let me just go a bit into the proof so we can actually do a bit of the quasi-transitive graphs, and we will just close the talk. So, okay, so the proof contains two parts. And one of them, as usual, is a bit easier. So the easy one is that one implies two. Okay, so first one is one implies two, so we're going to prove everything that we have there. Okay, for quasi-transitivity, well, quasi-transitivity is immediate, right? Because if we assume one, there's already a group that's acting quasi-transitively. That means that the whole automorphism group has to act quasi-transitively. To show that...
Why is it the case?
So...
It can be a different group.
Yes, but the automorphism, in particular, when FD acts on G, it means that this group FD, there is a copy of it inside the automorphism group of G. So this is saying there is a subgroup in the big automorphism group that has finite orbits. Therefore, when I act by the bigger group, the number of orbits can only reduce. So it stays finite. Quasi-tree. The fact that it's a quasi-tree comes from the fact that we have a free action and quasi-transitive. So quasi-transitive implies that there is a fundamental domain which has bounded diameter. We're taking locally finite, so nothing can go wrong in that way. Quasi-transitive implies there is a fundamental domain of bounded diameter and now the free group is acting freely when we look at this group of bounded diameter. So like at this fundamental domain. So like in the case of like this 3-4 guy that we were considering, what am I doing here? Yeah. Or whatever it is, I'm not going to paint it very precisely. There is this fundamental domain, which is like some sort of blob, and the free group is giving me translations of this guy in a way that I get the Cayley graph of the free group when I'm acting in this way. So the only distortion that I have between a free group and the whole graph is just this blob, this big bug that I'm considering here. And that's why I'm staying within a bounded distance of the tree, which is the Cayley graph of the free. So fundamental domain of bounded diameter plus free action of FD, which is a tree. And now to check unimodularity, Well, we didn't do this, but of course now I can just take the map that goes from G to the quotient graph by the action of Fd. And this graph is a finite graph because I have a quasi-transitive action. And it shouldn't be, it's a fact that all finite graphs are unimodular, okay? Why is this? I can say this quickly. What measure do you take? You just take the counting measure, okay? So your probability mu on a finite graph is every type of vertex, how many times does it appear? And then once you unravel this equality, it just says on one hand you have a double sum, on the other side you have a double sum, both sums are finite, and the only thing you need to change is order of summation. So finite graphs are unimodular. I can define a measure mu here for the types of vertices, and I can use these weights to define corresponding weights in here. Okay, so this is an exercise that you could do, for instance, with the 3-4 regular tree that we had before. You go to the complete graph on 3 and 4 vertices, and then you just count how many vertices of degree 3 are there, how many vertices of degree 4 are there, and that counting is what gives you the probability that you need to put here. So this is just a simple exercise that proves that in this case, with this picture, you have unimodularity, okay? And now to close up, I will quickly sketch the other part. And this is the direction where Hugo helped us a lot with the proof to decipher. So like, the fact that I mentioned it before, there is this result of Hamann. I'm going to write everyone's name correctly. I have it somewhere. Hamann, Lehner, Miraftab, and Riemann. They have this result that says that when G, let me get it. Yeah. When G is as in here, it's a quasi-transitive quasi-tree. There exists a tree decomposition T and V. Is everyone familiar with tree decompositions?
Yes.
I guess so. Okay, yes. So we have the tree and we have the bugs. And what do we have? We have some properties. First one is the automorphism group of the graph acts on that tree, acts on the edges transitively. Transitively. This is finite addition, I think is called. Every vertex is infinitely many bugs. Every vertex is infinitely many bugs in V. And moreover, because we're in this situation of quasi-transitive quasi-tree and with locally finiteness, we can assume that there is each of the, there is a constant such that all bugs have diameter or really size. That's the only thing we need. At most K, for some K, okay? So using this result, now we can try to produce this free group. And this has to take this information and go through some group theory. But the idea is not, the whole core is in a paper of Bass and Kulkarni. So like, if I black box that, then the proof is not that complicated. So what we're going to do is the following. I'm looking at this guy. My aim is to produce a free group in here, okay? That's my goal. I want to produce a free group in here. So first I'm going to look at this group sitting in the automorphism group of the tree, okay? Because I know that, the automorphisms are acting on the tree. So in particular, I get a map, C, that takes an automorphism of G and sends it to an automorphism of T. Okay, and now I'm going to look at H. I'm going to look at this, which is going to be defined to be the image of C. Okay, so I'm going to look at this group. And now, on the one hand, and this is where unimodularity goes in yet another definition. G being unimodular is the same, if you're familiar with the theory of Hermessier, is the same as the automorphism group being unimodular. In the sense of Hermessier. What this means is that there is this Hermessier, which is a unique left invariant measure that you can define in these locally compact groups. So it's a measure here, and the group is unimodular when you can invert the whole group and this measure stays the same. And yeah, this is a group theoretic notion and analysis on groups, and this is really where the name of unimodularity comes from. Here, this was before in the literature, because there's some homomorphism called the modulus. And so what do we have? We have that the automorphism group is unimodular, and I want to say that H is unimodular, and I have this because H, by some isomorphism theorem, is isomorphic to the quotient of the automorphism group by the kernel of this Psi. But the kernel of Psi is, if you are an automorphism of G that leaves the whole tree invariant, this means that you are just permuting things inside the box of the tree decomposition, but each of the bugs is finite. So you can think of this kernel as a product of these finite groups. So this is compact, and therefore when you look at this hard measure that you have there and you quotient it out by this compact group, well, you're just sort of like doing a sort of contraction of something that has like some finite measure, and this preserves unimodularity. So this implies that H is unimodular. And now is when one brings the big box and the artillery, which is this theorem of Bass and Kulkarni from the 90s. And this is really the heart of the proof that says when you have H acting on T a tree, locally finite tree, then H contains a free group acting on T freely and quasi-transitively if and only if H acts quasi-transitively and H is unimodular. Okay, and this is really the black box that exploits this notion of unimodularity of groups to say when you have your group acting on a tree quasi-transitively, when is there a free group? Well, there is a free group when this group is unimodular. You need that unimodularity. This is an if and only. And once you have this, then we can sort of just go back. Okay, so what does this imply now? Therefore, there exists some free group in H. So S1, SD for some D is a subgroup of H, which is free and acts quasi-transitively. On T, and now our desired subgroup is just any preimage of this guy, which is a free group. So let Si tilde be such that psi of Si equals Si, then if you take this S1 tilde up to SD tilde, this is a subgroup of the automorphisms of G, and it is free acting freely quasi-transitively. Let me quickly say why. The group is free because there's no relations in the image, so therefore there cannot be any relation between them. Why does the group act freely? Well, we look at the stabilizer of a vertex, okay? We know that each of these SIs, any element in here, acts freely on the tree. So we can look at the stabilizer of any vertex under these guys. But now we said that each vertex is infinitely many bugs. So the only thing that can happen is that the stabilizer of this vertex stays inside. It's a permutation of these finitely many bugs it belongs to. But this means that the stabilizer, because the bugs are finite, the stabilizer is finite, but stabilizers are subgroups, and there is no finite subgroup of a free group because they have no torsion. Therefore, this argument shows that the action is free, and then quasi-transitively just comes from the fact that because this group acts quasi-transitively on the bugs, and the bugs are finite, so they have some finite number of elements, then you just multiply by this, and you just some larger number of orbits, but finite. And that is end of the sketch, and I think that's a good time to conclude.